We've used two fixed pulleys attached to the ceiling and two movable pulleys hooked onto their bike. The fixed pulleys make it easier to pull the bike up by changing the direction of the force so he can pull down instead of having to lift the bike up. But the movable pulleys give him a mechanical advantage too. An exercise machine is a great example of a pulley system. If you can get to a gym or a community center that has weightlifting machines, check out the pulley system on the machine. What is the mechanical advantage? Why are they using pulleys? On your own, draw the machine in a quick sketch and determine what the advantage to using this system might be over just lifting free weights. Why do the cables need to be so long? Instead of an axle, the wheel could also rotate a rope or cord. This variation of the wheel and axle is the pulley. In a pulley, a cord wraps around a wheel. As the wheel rotates, the cord moves in either direction. Now, attach a hook to the cord and you can use the wheel's rotation to raise and lower objects. On a flagpole, for example, a rope is attached to a pulley. On the rope, there are usually two hooks. The cord rotates around the pulley and lowers the hooks where you can attach the flag. Then rotate the cord and the flag raises high on the pole. A single pulley simply reverses the direction of a force. When two or more pulleys are connected together, they permit a heavy load to be lifted with less force. The trade-off is that the end of the rope must move a greater distance than the load. A block and tackle is a set of pulleys assembled so they rotate independently on the same axle from a block. Two blocks with a rope is attached to one of the blocks and threaded through its pulleys from a block and tackle. A block and tackle is assembled so one block is attached to a fixed mounting point and the other is attached to the moving load. The mechanical advantage of the block and tackle is equal to the number of parts of the rope that support the moving block. Review these images of various block and tackles. Determine the number of strings that are helping to lift in each of the figures. Input the correct number of strings that are helping to lift in each of the figures. The rotation of the lever against a point pries objects loose. That rotation motion can also do other kinds of work. Another kind of lever, the wheel and axle, moves objects across distances. The wheel, the round end, turns the axle, the cylindrical post, causing movement. On a wagon, for example, the bucket rests on top of the axle. As the wheel rotates the axle, the wagon moves. Now place your pet dog in the bucket and you can easily move him around the yard. On a truck, for example, the cargo hold rests on top of several axles. As the wheels rotate the axles, the truck moves. In this machine, a wheel or spoke is locked to a central axle so that when one is turned, the other one must turn. A longer motion at the edge of the wheel is converted to a shorter, more powerful motion at the axle. In reverse, a short, powerful force at the axle will move the wheel's edge a greater distance. Though these devices were also used in machines in Leonardo da Vinci's time, he experimented with them and made changes to improve how they worked. He also combined them in many exciting new ways to create machines and inventions that had never been seen before. Click on each of these elements to learn more. Leonardo's fascination with machines probably began during his boyhood. Some of his earliest sketches clearly show how various machine parts worked. As an apprentice in the studio of the artist Verrocchio, Leonardo observed and used a variety of machines. By studying them, he gained practical knowledge about their design and structure. Artists and craftsmen in Leonardo's time knew how to build and repair the familiar kinds of machines. The idea of inventing new kinds of machines, however, would have not occurred to them. Leonardo developed a unique new attitude about machines. He reasoned that by understanding how each separate machine part worked, he could modify them and combine them in different ways to improve existing machines or create inventions no one had ever seen before. Take a few minutes and explore this site and play with the materials. It is a neat experience to see how some of these gadgets work. Then you can return to this lesson and continue with another project related to simple machines. Here's an activity students can try on their own. Sketching a gadget's anatomy. The main idea is to make detailed and close observations and sketching which will lead to a better understanding of how unique and unusual machines work. You are improving your observation skills. The objectives for this project include: observe a machine closely from several angles while it operates. Identify the elements of machines combined in different gadgets. Show how the moving parts in machines relate to and affect each other, and create a clear diagram of how a machine works. Possible materials you should gather include paper, pencils with erasers, and copies of the inventor's toolbox pages for reference, and a selection of small machines with visible working parts. Carefully look about your home or business. Here's a list of some examples that might work. Once you have found your machine, examine it in detail. Be sure that you operate the machine to watch to see how each part moves. Challenge yourself with the following questions to encourage thought and also investigate your own questions as well. Many of the published Leonardo resources in the bibliography section of the Leonardo website at the Museum of Science contain examples of his work that students will understand better after they have tried this activity. You may want to see how other artists have created diagrams of machines. David Macaulay's book, The Way Things Work, also contains many wonderful and whimsical examples. Have you located examples of machine diagrams at your home or in your wind energy classes? The instructions provided by manufacturers with bicycles, kitchen appliances, tools, and lawnmowers often contain explanatory diagrams to help you understand these machines. Auto repair manuals also contain dozens of these diagrams. Many construction sets, such as Lego and K'NEX, had similar kinds of diagrams to help you build particular toy designs when you were a kid. If you search the internet and find several diagrams from different sources, compare them and create a detailed analysis of them using the following questions as starting points. Which elements of machines do you see in each gadget? Click on only the ones you see. Use the materials left over from a project or from a trip to the local dump. Create and build a machine that makes at least one motion. Oftentimes, as a final project in applied physics, students make a mousetrap car or similar small machine that moves, delivers something from one spot to another, etc. Then make a video to present your machine. Show how it works, and give a demonstration which you can record on video. This can be difficult for some students because it might be the first time they actually had to build what they had designed. Many of the designs start out as very complex creations, and soon a student realizes that their design is too difficult for them to build. Hence, you can revise your creations many times, and in some cases, the final result looks very little like the original design. Have fun and good luck with your simple machine. Good luck as you move forward on the next project and assignment from your instructor. In this lesson, you covered the following objectives.